Okay. First of all, I would like to thank the organizer for inviting me to this conference. And also thank you, Hao Zhong, for the nice introduction. Today I'm going to talk about a very recent work that hasn't been hasn't been put on archive yet. We plan to do that in the coming week. This work is done with my collaborator, Ryu Hayakawa. He was a PhD student in Kyoto University, and from this April, he became a research professor in University of Kyoto. And also a group members in our Foxconn research, Guojin, Chen Guojin. Guojin's research was focused on quantum work, so I would say that Liu and Guojin are the main driving force of this research outcome. Okay, so this is the talk outline. Of course, I would give a short motivation and then give you the main result of our work. And then if I have time, then I would go over those steps that how we prove it, so in the second items. And then we will show that how to apply it, our quantum work to resolve to provide interesting applications. Okay, so from the title, you can see that this talk regards about the topologies. This is like an area in pure mathematics. Topology is very useful, and it has applications in many applications. But today I'm going to only focus a slightly narrower focus. That is whether topology would assist us in data analysis. And of course, the answer is yes. And in the classical data analysis, this has been evolved into a subfield that is called the topological data analysis. Of course, that later on I will show you that finding the topology features of your data is very, very difficult classically. And that's why this motivates us to look at a quantum algorithm, and hopefully our quantum algorithm provides speed up. Okay, so what is the goal of topological data analysis? So from here you can see that given some data, right, and the idea is that we try to map data into shapes, right? So the way to do it is that from a data point, then you can assign a radius, right? And by slowly increase the radius, right, then some of the data would touch upon each other. So the balls surrounding this data point, they would overlap. And then you can start to form high-dimensional object, right? So for example, this triangle here exists because that's three balls touch upon themselves. And the reason that we want to do that is that by this, you can see that some of the data points actually have stronger correlation. So they have higher dimensional correlation than just vertices and lines. So for example, this purple one is called the four simplices, and I would give a formal definition later on, and it tells you about this higher dimension correlations of your original data. And then from this the topology of the shape, then we look at some of the features that from them, and from the features, then hopefully it would give us like hidden information in the data. So we can perform this analysis to look at relevant topological features, and I will show you what what kind of features that we care about, and also like the areas that TDA, topological data analysis, cares about. And the reason that, and this is quite interesting, so you can see that from like you can transform a donut to a mug without changing actually its topological features, right? So this example, I want to use this example to shows you that while if you, in the first look, like you see these two objects are different, but in fact they have the same topological features. Okay, so in this talk, we would mainly care about these topological features that's called, that is the k-dimensional holes, okay? Like if you use this jargon in the topology, this is called, this is equivalent to the k-Spati number. So the reason we look at this is this give you the indication that this correlation only exists in k-dimensional, not k-1 dimensional, okay? And these are a few examples for these Spati numbers in small dimension, because when it goes to higher dimension, we won't be able to draw it. And so that's why sometimes topology is hard to imagine. It's because of this. It's hard to draw in a 3D world. So, so the zeroth Betti number is just connected point. So it's a vertices or it's a dot. And the one-dimensional hole, beta 1, is just a circle. So, so in this case, that you have a connected component. So beta 0 is 1, beta 1 is 1, and so there's no, the beta 2 is 0. So beta 2 means that it has the empty interior. So for example, sphere has an empty interior, so its beta 2 is 0. Same for the torus. Torus has one empty interior, but it has two circles. So one along this direction and the other along this direction. Okay? So like I said, counting or calculating the Betti number is very difficult. So, so this is a very recent result published in PRX Quantum, saying that to exactly calculating the Betti number is sharply hard. Before this result, we also know that if you want to compute certain Betti numbers, it belongs to P space, right? And anyway, if you are not from the complexity theory, I mean, this means that it's very difficult to do the calculation. And then we also know that the promise click homology problem. So this means that, again, this means that given K, given a K homology, K simplexes, to decide whether a K-dimensional hole exists or not, this is also very difficult. So this is QMA 1 hard. And again, this result is fairly recent. But there is a good news, at least in the quantum domain. So if you want to compute the normalized version, so when we say normalized version, it means that you normalize this beta k by the number of homologies in it. So, and to estimating normalized Betti number, this is DQC1 hard. That means that it can be computed using one clean qubit quantum computation model. Okay, but normally we believe that problem in DQC1 is also hard to compute classically. So I mean, in a sense, I consider this is a quantum advantage. Yeah. Okay, so before I introduce some of the known results using quantum algorithm to compute those topological features, I need to first formally define some terminologies. So, so this is the definition